I'm thrilled to share with you some of the work that my lab has been doing with the sponsor of the Arnold and Mabel Beckman Foundation. My lab is at the intersection of organic and supramolecular chemistry, material science, and physical organic chemistry, and we are developing new molecular tools to engineer new materials relevant to energy conversion. Today, I will show you the approach that we have been taking towards engineering new classes of piezoelectric materials. So let me dive right in. Piezoelectric materials enables the conversion of mechanical forces into electrical energy, and they are exclusively observed in materials that features non-centrosymmetric architecture with microscopic polarizability. What does that mean? That means that molecular dipoles need to be aligned and point to the same direction across microscopic dimension. There are many limitations with current technology, and one of the challenges that we have isolated was to engineer new classes of ionic organic materials that feature non-centrosymmetric organization. And I can summarize this challenge in the next cartoon. If I'm taking a molecular dipoles where we have part of the molecule that is positively charged, the other one negatively charged, if I'm packing these molecules into the solid state, I will basically form a centrosymmetric 3D arrangement because opposite charge attract each other. And really the goal of the Beckman-Young Investigator project was to design and come up with a general molecular roadmap that can take any type of molecular dipoles and organize them into a non-centrosymmetric 3D arrangement. So how do we go about it? The first step was to functionalize a monolayer with molecular dipole, because this type of conformation already evidence a non-centrosymmetric arrangement. Then the next step was to polymerize and desorb the monolayer to create two-dimensional nanostructure templates that we can use as seed to self-replicate this non-centrosymmetric organization and expand it across mesoscale dimension in order to create a large quantity of these materials and eventually organize them in the solid state to engineer mechanical energy harvester and electronic skin. And really what I'm going to show you over the next couple of slides is this first step here that we've been designing and pioneering of forming monolayers and polymerizing them and desorbing them from the surface. We have developed methods to functionalize silicon surfaces with redox active probes to quantify surface coverage using electrochemistry. And the surface and the probe, the electrochemical probe I'm referring to is this entity over here. And basically what we have been doing, we can calculate using cyclic voltammogram the coverage of the silicon surface with this building block. And that's very important for us because keep in mind that we want the highest number of molecular building blocks as possible. And what we quickly realized is that by using these strategies that I'm showing you here, we are accessing a surface coverage of one molecule per 35 nanometers square. And that was not high enough because keep in mind that we need to polymerize whatever we're anchoring on the monolayer. And so after some trials and error, my postdoc Arindam has come up with an amazing way of doing this. And what he decided to do is to switch gear and use what we are calling thiol-ion photoclick, using as precursor this surface that I'm showing you right there. And so by using that, what we can do now is we can access a surface coverage of around one molecule per nanometer square. And now that's really fulfilled the requirement that we have initially of having a high density of redox probe per surface. And more importantly, we also have this ester function that I'm showing you right there that we can further hydrolyze to desorb this entity that is anchored on the silicon substrate. And that's going to become important for the desorption part. Thiol-ion reaction can be used to further increase the density of anchor redox probe by using the sequential approach that I'm showing you here that we are calling thiol-ion and thiol-in. And using cyclic voltammetry, we can probe, looking at this electrochemical signal, the conformation of our bilayer at the interface. And the punchline here is that by using this sequential functionalization methodology, we can access a very high surface coverage that will become very handy to polymerize the monolayer at the interface. We have been using this tool to build 2D nanoscale objects from the monolayer precursor that I'm showing you right there. And using this tripodal molecule using a thiol-ine and thiol-in, what we are doing is we are reticulating our building blocks on the surface itself, and we are leveraging the ester function I'm showing you here to desorb the reticulated monolayer. Now, of course, one limitation of this approach is the quantity of this monolayer that we're forming is really small, and we had to develop new class of supramolecular assay to be able to indirectly characterize our material. And so to do that, my really talented postdoc and graduate student, Ifi Tsioni, they decided to use multivalent interaction, because keep in mind that the polymerized desorbed monolayer has a multitude of negatively charged functional group on one side of the monolayer. And by using a surface that is positively charged, we can fish out these materials out of the solution, and we can characterize them using spectroscopy or microscopy. Just to give you an example, we can detect layered structure by atomic force microscopy, and that's what I'm showing you here, depending on the solvent. And these layered materials are completely absent for the controls. And that tells us one thing, that tells us that whatever we're forming and polymerizing on the initial silicon substrate can be desorbed and reabsorbed on another substrate. And that's very important, because it really shows us that this vision that we had and that we pitched to the Arnold and Mabel Beckman Foundation about forming monolayer and polymerizing them on the surface is actually a valid approach to design 2D nanoscale objects from the bottom up. Now, this project has completely opened new avenues to design, for example, non-volatile electrochemical memory devices that we have recently published, as well as using this platform to trap and probe the electronic structure of intermediate. And we can also use orthogonal surface chemistry now to probe light matter interaction at nanoscale interface. And that's a collaborative work that is currently undergoing with Eric Grumstrub, a former BYI 2017. And this project has been recently been funded by the NSF. And I think this shows how important the Arnold and Mabel Beckman Foundation is for young investigators, because it really nurtured the collaboration that wouldn't have existed otherwise. To conclude, I want really to thank my group, and particularly Arindam, Ifi, and Victor, who are instrumental in developing the science that I've been showing. I also want really to thank the Arnold and Mabel Beckman Foundation for their support, kindness, and generosity, especially during the COVID time. And before I go, I just wanted to give you a few concluding remarks. Throughout his life, Dr. Beckman has made tremendous contribution to science with the invention of the spectrophotometer and this pH meter. My lab is using it every day. But I think, in my opinion, he has also shown that believing and investing in people is equally important to great science. And I think this is a very powerful lesson that I am taking with me.